Imagine working on a project you know you have no hope of seeing through to completion. Would you even have the motivation to begin? For Ralph McNutt, a scientist at Johns Hopkins University Applied Physics Laboratory in the United States, the answer is an unwavering, absolutely. In 1977, the Voyager 1 and 2 spacecraft were launched from Earth on an ambitious mission to explore the outer planets of our solar system, starting with Jupiter and Saturn. This was a monumental task. No human-made object had ever embarked on such an extensive journey into the cosmos. The mission marked a groundbreaking chapter in space exploration. Voyagers 1 and 2 were equipped with advanced instruments and cameras that captured tens of thousands of images, offering humanity its first detailed glimpses of the distant giants and their moons. These images revealed the intricate swirling clouds and massive storms of Jupiter, including the iconic Great Red Spot. The spacecraft also provided unprecedented views of Saturn's complex ring system, showcasing the delicate structures and gaps within the rings that had never been seen before. Beyond imagery, the Voyagers made remarkable discoveries that transformed our understanding of the outer solar system. Voyager 1 and 2 detected active volcanoes on Jupiter's moon Io, making it the first body beyond Earth known to have volcanic activity. Voyager 2, continuing its journey, became the first and only spacecraft to visit Uranus and Neptune, capturing images and data that unveiled 22 previously unknown moons and the icy blue hue of Neptune's atmosphere. The Voyager missions once again made history in the 2010s. Voyager 1 became the first spacecraft to exit the Heliosphere, the vast bubble of charged particles and magnetic fields influenced by the Sun, and enter the interstellar medium. This region, dominated by particles, dust, and magnetic fields from other stars, is a frontier never before explored by human technology. Voyager 2 followed, making them both pioneers in interstellar space. Today, more than 4 decades after their launch, these intrepid explorers continue their voyage through the cosmos. Voyager 1, having traveled over 23 billion kilometers from Earth, is about 155 times the distance between the Sun and Earth, a distance scientists refer to as an astronomical unit. Both spacecraft remain in interstellar space, the vast expanse between stars, and no other spacecraft has ventured this far from home. Despite the unimaginable distance, Voyagers 1 and 2 are still sending valuable data back to Earth, helping scientists learn about the conditions at the edge of our solar system and in the interstellar medium. Their power supplies are expected to last until around 2025, after which communication with Earth will eventually cease. Yet, even after their power fades, the Voyagers will continue their silent journey through space, passing by other stars over thousands of years, carrying with them the golden records, messages from Earth to any potential extraterrestrial life they might encounter. While the primary mission of the Voyagers was to explore the outer planets, they have inadvertently provided a wealth of information about the galactic environment in which our Sun resides. However, the spacecraft were not specifically equipped to study the heliosphere's boundary in detail. Recognizing the need for dedicated exploration of this frontier, scientists are now developing the Interstellar Probe, a next-generation mission designed from the ground up to explore the space between the stars. This future mission promises to unlock even more secrets of the universe, continuing the legacy of discovery that the Voyagers began. Our Sun is just one of over 100 billion stars in the Milky Way galaxy, moving through a vast sea of interstellar gas, plasma, and dust, material born from the explosive remnants of ancient supernovae. With its ever-pulsing solar wind, the Sun carves out an immense protective magnetic bubble known as the heliosphere, which envelops the entire solar system. This heliosphere is not just a shield, it defines the boundary between our solar system and the interstellar space beyond. Understanding the complex interaction mechanisms at this boundary remains one of the most enduring challenges in space physics. These same processes are responsible for shaping the astrospheres, protective bubbles, around countless other stars and exoplanetary systems in our galaxy. Beyond the protective cocoon of the heliosphere lies the local interstellar medium, LISM, an uncharted realm filled with mysteries that influence the shape, size, and behavior of our heliosphere. The LISM is a frontier that has remained largely unexplored, despite its crucial role in determining the conditions at the very edge of our solar system. The local interstellar medium, LSM, refers to the collection of gas, dust, and cosmic rays that exist in the space between stars within our galactic neighborhood. It's like the stuff that fills the voids in space around our solar system, playing a crucial role in shaping the environment through which our solar system travels. Within this vast region, our solar system is currently moving through a small area known as the Local Interstellar Cloud, LIC. This cloud is a denser, warmer part of the LSM, composed mainly of hydrogen and helium, and it influences the heliosphere, the bubble-like region dominated by the solar wind. The LSC is part of a larger structure called the local bubble, a cavity in the LSM created by supernova explosions. The interaction between our solar system and the LIC impacts cosmic radiation levels and could have subtle effects on Earth's climate over long periods. The idea of sending a mission into the local interstellar medium has intrigued scientists since the dawn of the space age. The prospect of an interstellar probe capable of venturing beyond the heliosphere and into the LSM has driven scientific inquiry for nearly 6 decades. Numerous studies have identified compelling scientific goals and questions that such a mission could address, including those from pioneers like Holzer, Mewalt, and Neugebauer, 1990, and more recent efforts by Wang, 2018. Despite the passage of time, the core scientific questions have remained consistent, centering on the exploration of the heliospheric boundary and the properties of the ISM. A mission trajectory that takes a probe through the outer solar system and the Kuiper belt beyond our zodiacal cloud would not only explore the heliosphere's edge, but also unlock groundbreaking opportunities in planetary science and astrophysics. Even with modest instrumentation, such a mission could yield transformative discoveries. Building on decades of research and current collaborations within the scientific community, the present study has refined its science goals for a potential interstellar probe mission. This mission aims to answer a broad array of questions spanning multiple disciplines. Below is a brief list of the key areas of inquiry, each linked to more detailed descriptions of the proposed topics, including specific questions and objectives for each field. Our heliosphere as a habitable astrosphere and its place in the galaxy. How does our sun's protective bubble compare to those around other stars? What does this tell us about the habitability of exoplanetary systems? The origin and evolution of planetary systems. What can we learn about the formation and evolution of planets by studying the outer reaches of our solar system and beyond? How early galaxies and stars were formed. What clues about the early universe can be gleaned from studying the interstellar medium and the ancient remnants of stellar evolution? Ralph McNutt, along with his colleagues at the Johns Hopkins University Applied Physics Laboratory, APL, has published an ambitious proposal detailing a visionary project, a long-lived interstellar probe designed to journey into the vast space between the stars. While NASA's legendary Voyager spacecraft are already traversing this domain, McNutt's probe aims to venture even farther and faster, with the expectation that it could still be operational 50 to 100 years after leaving Earth.
Imagine launching this mission in 2036 and reaching the end of its nominal mission in 2086.
McNutt remarks,
I'd be about 130 years old by then, so it's not something I'll witness personally, but that's the essence of space exploration. You pass the torch. I always tell people, if you're into instant gratification, space exploration isn't for you.
It's important to clarify that this is not a mission to another star. Such a feat remains beyond our technological reach. The nearest star systems are simply too distant for a probe to arrive there within a human lifetime. However, this spacecraft would become a long-term traveler in the mysterious gap between the stars, an area still ripe with unexplored possibilities. Initiated at the request of NASA's Heliophysics Division, the current study dives deep into the engineering challenges of such a mission, culminating in a nearly 500-page report. The proposed concept features an 850-kilogram spacecraft equipped with advanced sensors designed to measure critical parameters such as charged and neutral particles, magnetic fields, and interstellar dust. The probe would be launched around 2036 aboard a super heavy lift rocket, augmented with additional stages to achieve an incredible escape velocity. The spacecraft would pass the Moon's orbit in just 6.5 hours and reach Jupiter within 7 months for a gravity-assisted slingshot maneuver, propelling it to a blistering speed of 6 to 7 astronomical units per year, over 1 billion kilometers every 12 months. Longevity, however, is key to this mission's success. Unlike the aging Voyagers, which are now prioritizing their remaining instruments as their radioisotope thermoelectric generators weaken, this new interstellar probe would be powered by 2 next-generation nuclear batteries, currently under development by NASA. These batteries are expected to provide enough energy to send data back to Earth well into the 22nd century, even as the probe ventures hundreds of AU away from our planet.
What our study has achieved is to take the dreams of scientists and apply the engineering needed to make them a reality,
explains Alice Kokoros, the payload systems lead for the study team.
What's exciting is that with near-term technologies, those that won't require significant new development, we can accomplish all the scientific goals we've set for this mission.
In addition to its primary mission, the probe could also perform a flyby of a significant object on its way out of the solar system, should funding allow. This could mean revisiting Pluto, which was first explored by the New Horizons mission in 2015, or possibly rendezvousing with one of the icy bodies in the Kuiper Belt, a region still shrouded in mystery. But the true treasure lies beyond the heliosphere. The data returned by the Voyager probes has sparked numerous new questions about the nature of the Sun's protective bubble, according to project scientist Pontus Brandt.
Some 4.6 billion years ago, our solar system began to take shape, and with it, this magnetic bubble that shields us from the dust and plasma as we travel through the galaxy. An interstellar probe would help us understand not just our current state, but also our origins, the impact on evolution, and where we're headed next. Not many realize that we're on the brink of exiting our local interstellar cloud, a region the heliosphere has been plowing through for the last 60,000 years, and entering entirely new territory.
Whether this interstellar probe secures the estimated $1.6 billion in funding will depend on the broader support of the solar and space physics community in the United States and their prioritization of research goals. Meanwhile, other concepts are being developed globally. China is working on its own proposal, called Interstellar Express, and Russian-Israeli entrepreneur Yuri Milner has proposed the Breakthrough Starshot Initiative, a private venture aimed at sending a fleet of tiny star chips toward the nearest star system.
There are two things that truly inspire people,
says Pontus Brandt.
One is the desire to boldly go where no one has gone before, and the other is the beauty of a long mission, one that's undertaken for future generations. This is where the future of space exploration lies. We do this not just for ourselves, but for those who will follow.
Ralph McNutt echoes this sentiment, reflecting on the deeper meaning of such a mission.
It's not just about the destination, it's about the journey itself. And this is a journey that is long overdue.
As we conclude this virtual odyssey, we invite you to like and subscribe to our channel to embark on further cosmic explorations. With every click, we elevate our pursuit of knowledge and contribute to the collective understanding